So to return to the previous hour, there's something I forgot to explain. Why did you learn at the fundamentals of electrical engineering that it is impossible to make a discontinuity on the tangential electric field? You learned this, and you were told that it's impossible to make a discontinuity. And here we made a discontinuity with real devices, not with an imaginary magnetic current that does not exist, but with a real electric current. Why is this impossible for DC? If you look at the equation we got down here, what should we replace the magnetic current with? This thing here has K in the numerator, in the denominator. The denominator has K, so K is omega divided by C0. K is frequency. If we put the frequency to 0, what we get for our current? We get an infinite current. This is the reason why this cannot be done for DC. It can be done for radiation, for high frequencies, but not for DC, because for DC K, the wave number becomes 0, and with 0 the wave number, the current goes to infinity. This current of the loop, of the magnetic loop, of the small magnetic loop, becomes infinitely large. So we cannot do the jump of the tangential electrical component, the discontinuity, we cannot do it for DC currents. That's impossible. That's impossible because the current goes to infinity here. So this was something I forgot to tell you before. And this also explains why 3 years ago you learned things a little bit different as we are doing here. Everything is dynamic here. Everything has a frequency here, and things work out differently. And some things would actually here work, like radiation works, where 3 years ago you didn't even hear about radiation. No one told you anything about radiation. We are dealing with radiation all of the time. And also some things that cannot be made for DC can be made for frequencies different from 0. So now let's see, how do we calculate the radiation of this? We'll be more detailed for Horns next time. I'm only going to draw an aperture on the board right now. So we turn a little bit our coordinate system to actually ease the drawing. The drawing will be much easier here. So put the x-axis here, y-axis, and the z-axis. And here I have an aperture. Maybe a rectangular one, just like that horn. So this is a rectangular aperture. Like I'm going to integrate over this surface. I know that this surface radiates. There is no radiation from here or from here, just from the surface. And I'm only going to observe the surface. The surface that may have two sides, like this may be A side, so A half here, A half here, and B half here, B half here, a rectangle with sides A and B. How am I going to calculate the field? I'm going to put my Huygens source here. And this Huygens source is going to generate radiation over here. So I'm going to observe the generated electric field here. If I draw the geometry, so this is the distance r. The position of my Huygens source is r prime. So if I draw a vector, I should write also a vector sign here. So this is vector r. And this distance here is r minus r prime, absolute value. Okay? So this is angle theta. Is here. And my Huygens source has differentially small size of dx and dy. I can go differentially small, that's no problem. So my dE here what is it going to look like, dE? First, I said I'm only interested in far field. No near field, because near field is complicated and it's useless. So for far field, how can I write this dE? I'm going to write dE without the vector sign, so I need not deal with polarization. It's the same for all polarization. It's j over 2 lambda. Then it's E0, but this E0 here that I have on the surface, I have E0. Maybe a function of x prime and y prime. So x, y, and I prime together make r prime. May not be constant over the aperture, okay? May not be constant. Dx, dy. I also have the radiation term, E. Exponent of a minus jk r minus r prime divided by r minus r prime. And here I have 1 plus cosine theta, the radiation pattern. If I were accurate, I should really talk here about theta prime, because theta also changes a little bit. But this change is insignificant in the far field, because in the far field, the radiating aperture looks very small, and all the possible thetas are very, very small. So I should really draw here normal here, and I should draw here theta prime. And to be accurate, I should use here theta. So a simplification for the far field, what does it look like? dE for the far field, simplified. Okay, j over 2 lambda stays where it is. E on the aperture of x prime, y prime. These are the coordinates. Dx prime, dy prime. Of course, I have to integrate. I will integrate over the aperture. Dx prime, dy prime. This is dx prime, dy prime. The amplitude does not change much in the far field. So in the denominator, I can just replace by r this thing here. But in the numerator, I have to be accurate in the numerator. And in the numerator, I have to rewrite this r minus r prime. This is approximately r minus x prime times sine theta cosine phi minus y prime sine theta sine phi. It's the projection of this small offset, but this thing actually counts in the exponent. Counts in the exponent, so I can write the first term. The first term here is e to the, okay, I will write it complete. E to the minus jk, and I have r minus x prime sine theta cosine phi, and minus y prime sine theta sine phi. Okay, 1 plus cosine theta. What are these projections? I wrote here in such a strange way. So this is actually cosine of theta x. And this is actually, this thing here is cosine of theta y. Maybe I should draw it in this way because it's much easier to write everything on the board using this notation. We already did this projection with the half-wave dipole. Exactly the same thing, but the half-wave dipole was just in one direction. Here I have in two directions, in the x and y directions. With the half-wave dipole, I only have cosine theta in the z direction. So now, how do we calculate the total radiated field? The total radiated field is now the integral over the aperture A, this is the aperture, of dE. Now, here I have really many constants that I can usually take out of the integral. Like j over lambda, 2 lambda is a constant. This is not a constant. This is the differential of the integral. Here I have something constant. I have e to the minus jkr over r. And then I have an integral from minus a half to plus a half, from minus b half to plus b half, of what? Of field on the aperture. So this is illumination of our aperture. I have two exponent function, e to plus jk now, to account for 2 minus signs, I have plus jk. I will write here cosine theta x, just to not have such a long expression here. E to the jk cosine theta y. This is the second term. Sorry, I forgot here x prime and y prime. Oh no, have to rewrite everything. So here was x prime cosine theta x, e to the jk y prime cosine theta y, dx prime dy prime. So in this way, I can calculate the whole radiated field. And something I forgot here, this term, 1 plus cosine theta. So 1 plus cosine theta, I forgot it here. Forgot to write this one here. So this is constant with respect to our integration, so we can simply put it in front. Now the question is to evaluate these integrals. What am I going to do right now? I have to assume some illumination pattern. And now the simplest thing to assume is that our aperture is constantly illuminated. I have constant illumination. So now assume our example. We assume that this illumination of x prime and y prime is constant. If this constant is simply sum E0, okay? So this is a uniformly illuminated aperture is something we like to use. This is not an invented example. It's what we would like to have on many occasions. So if I rewrite now this equation, so E is equal to what? Without the vector sign, because we are not dealing with polarization. So E is now equal to J E0 over 2 lambda if the illumination is constant, e to the minus jk r over r, 1 plus cosine theta. And then I have two similar integrals, the integral over x prime and the integral over y prime. So I have the first integral over x prime. So this on x prime, I go from minus b half to plus b half, e to the j k y prime cosine, x prime, sorry, x prime cosine theta x, because x goes from minus b to plus b half, the x prime. And the second integral is integral from minus a half to plus a half, e to the j ky prime. This was x here. X, y, cosine theta y, dy prime. These two integrals have similar solutions. So let's try to solve just one of these integrals, because we need not both integrals to solve. What is the solution of this integral? What is this equal to? This equals, say, I'm going to write here the solution. The integral of an exponent function is 1 over everything else, so j, k, cosine theta x. And the same function as we had, so e to j, k, x prime cosine theta x in the limits from minus b half to plus b half. Okay? That makes sense. So, if I rewrite this here, I have j, k cosine theta x in the denominator. In the numerator, I have a to the j, k b half cosine theta x, minus on the lower bound is a to the j k, minus b half now, minus b half cosine theta x. Okay? So, I can make some space here on the board to integrate this. The difference of two exponent functions with opposite arguments is 2j sine of the same argument. So sine of k b half cosine theta x, and in the denominator I'm left with the j k cosine theta x. Okay? So, oh, here, the parenthesis is missing. So j cancels out. K, with k, and I have 2, I would prefer to multiply on top and in the bottom with b. So I have b times, now, sine of kb half cosine theta x. And in the bottom, I also have a similar expression, kb half cosine theta x. So I used these two to go to a double fraction here. And to have kb also in the bottom as in the top, I have to add another b in front. So I can write now the whole solution. The whole solution is j over 2 lambda E0. Now one integral gives b, the other integral gives a times b. Okay? E to the minus jkr over r, 1 plus cosine theta. But there are two of these functions. There is one function here, sine of kb half cosine theta x over kb half cosine theta x. And the other function is sine of ka half cosine theta y over ka half cosine theta y. So what is now our radiation pattern here? This is the radiation of our aperture. this is actually our whole radiation pattern. So radiation pattern of theta and of phi. So now we want to see what is going on here, what is actually happening here. As we increase B and as we increase A, cosine theta x and cosine theta y, what do they mean? Cosine theta x means rotating our antenna around the y-axis, so going around here so theta x I measured from here to the direction, so theta x is here. Theta x. So this will be the same as rotating my antenna around the y-axis. And cosine theta y is here. So theta y is here. So in one plane and in another plane, for instance, I measure the E plane and the H plane of this horn. The two planes I measured, okay? And how does this thing looks like? How does this thing look like? I will just draw one here. Up here I have some space on the board, so I can just draw one of these two terms here. The maximum of sine x over x, sine u over u, or sine v over v is 1. I hope you know that. So I could call this function something like sine u over u, and this is sine of v over v. Okay? These two functions. So I know what this function looks like, and where do I go for my theta cosine theta x? For cosine theta x, I go from 1 to minus 1. So if I draw here theta x goes from 0 to p. P half, it is p half cosine is 0. So if I write just here cosine theta x with the green cosine theta x. With green, cosine theta x is such a function, okay? This is cosine theta x. What happens with the pattern, with this sine u over u? This pattern becomes something like this one. Here goes to 1, or better to say to 2, goes up to 2, because this one with theta is 0 is equal to 2. And we get this familiar sine of theta x over x. We get a much narrower radiating globe. So the radiating globe actually becomes sharp here. When it becomes sharp, when we have lots of oscillations. When do I have lots of oscillations of sine u over u? When b is large. When b is large, the argument of this sine u over u will be very large, and we have lots of oscillations. So the larger the b, the narrower the pattern. And the same in the other axis, in the other plane, if I had, for instance, E and H planes for the antenna I measured in the lab. So choosing large B and large A, with B, I shrink the radiation pattern in the x direction with B, and with A, increasing the A, I shrink the radiation in the x. I shrink with A, I shrink the radiation in the YZ plane. So I can get arbitrary directive antennas in this case. Choosing large B and large A, I can shrink my radiation patterns so to have a very narrow beam radiated out of such antenna. If I have, of course, constant illumination of the aperture, and we'll try to do that on many occasions later on. In this course, we'll try to get the best possible illumination, possibly quite constant illumination. So in this way, I can improve the directivity. So if B raises, if B is increased, also the directivity is also increased. And also if A is increasing, also the directivity is increasing. We finally have a simple formula how to increase the directivity. But we still do not know what did we gain out of this. What did we gain out of this increase in directivity? How much increase in directivity are we going to get out of this? This improved narrower radiation pattern. What are we going to get out of this? And now for the directivity, what we have to do? For the directivity, we can use the standard formula for directivity. As we developed for an arbitrary radiation pattern, so directivity is equal now 4 pi f of theta maximum phi maximum divided by squared, of course, divided by the integral over the whole 4 pi solid angle f of theta and phi d omega, d solid angle. And of course this is also squared, because we need the power pattern, we need the power pattern. Actually, the power pattern, we don't need here the the amplitude pattern. Power and power absolute value to get rid of the complex values we might get out of here. Okay, this is a standard formula. It can be applied to this radiation pattern here. There is no problem. This can be applied. But there is a problem in the calculation of this thing here. This thing here, this sine of u over u squared, integrated over theta and phi, it's a terrible calculation. It's not an integral we can solve. But we could think this thing in a little bit different way. So how about having on top the same 4 pi f of theta maximum phi maximum? That's easy to compute. But on the bottom, I need not integrate over a distant sphere in the infinity, in the far field. I can, why did I did this integration in the far field? Integration in the far field over the whole solid angle of 4 pi, I did just to get the power, the radiated power. But on the other side, phi max, parenthesis missing here. On the other side, I can obtain the same power in other locations. And something that may be very easy, this power may be obtained somewhere else. Maybe obtained like integrating here on the only on the aperture, because on the aperture I have this E0. If E0 is constant, it's even easier. It's just a multiplication, not the actual integral. The multiplication. And so I have the whole power. Here are simply yes, the whole power divided by, so I need the whole power. So this is actually So it's maybe better to rewrite this in a slightly different way. So have the obtain the power over here. So to obtain the power over here, I simply can integrate this E0 of replace this. I need the whole power divided by 4 pi. So it's I have wrong things here. So here I should say integrating the Poynting vector, taking the Poynting vector as max of theta and of phi. No, sorry, I wrote this in a slightly cumbersome way. So to get the directivity in this way, take the S maximum of theta max phi maximum absolute value divided by the average S, and without the square here. This is just X is Z without the square because it's S, and down taking the whole power divided by 4 pi r squared. That is a possible solution. And how does this possible solution apply to our problem? How do we get S? S we get by squaring the power. So the Poynting vector is actually always direction 1r. Squaring the power means E squared divided by 2z0, okay? We can look what this turns out. Okay, 1 r, the unit vector is eaten by the absolute value. 2,0 is in the denominator, goes to the denominator. What is our power squared? Our power squared, if I take it here, I know that theta max is equal to 0. Is equal to 0, at least if I have this example, if this is constant. So if the whole aperture is illuminated in phase, then I get theta maximum equal to 0. This simplifies this term here, 1 plus cosine theta. So is E squared, I have it here. So J goes away, E squared, E0 absolute value squared, over 4 lambda squared, okay? If I calculate this, then this goes away with the absolute value, 1 over r, so r squared in the numerator. R squared in the numerator. This 1 plus cosine theta, this is equal to 2 because theta is equal to 0. Cosine theta is 1, so this is times 4 here, okay? Then I have the radiation pattern. The radiation pattern is actually this, this integral here. So in the integral over the whole aperture of the here I already made the assumption that it is constant. If I don't want to have it constant, I have to write here 1, and I have to have E0 of x prime y prime in the integral. These two exponents go to 0 because x prime is 0 and y prime is 0. dA of the aperture A, and this thing is squared. Sorry for this mistake. I already assumed that we have a constant E0. And in the numerator, what I have in the numerator? In the numerator, I have the power that flows through this aperture. Okay, divided by 4 pi r squared. I'm just taking this one. And the power is actually the integral over the surface of the S0. S0 on the aperture. S0 on the aperture is 1z times E on the aperture of x prime y prime squared 2z0. So this is integral over A over this of this S. So this S is now E0 of x prime y prime squared over 2z0 dA. I still forgot something. I forgot this. Okay. I still miss something here. I missed this 4 here that came out of this term here. I miss this one, where this one comes from. No, it's correct. It's correct. Everything is correct here. So now let's see what cancels out here. This r squared and r squared cancels out. Then this 2z0 and 2z0 cancels out. And this 4 cancels with this 4. Okay, everything is correct now. So if we go to look at what is left over now, we took the S maximum divided by the whole power getting through this aperture. This is the whole power integrated. This is the field squared. So let's see what happens, what we have here. We have 4 pi in the double denominator divided by lambda squared in the numerator on top. And we have integral over A, so of E0 of x prime y prime dA squared divided by integral over A. So 2z we cancelled out, so we have E0 of x prime y prime absolute value squared dA. This is now our shortcut for the directivity, not having to integrate this ugly thing here. So in place of integrating the whole pattern, I prefer to calculate the power getting through my aperture. So in place of integrating over an infinitely far away sphere, I integrate it over the aperture. And this is what I did here. This is now my final result for what condition? For the condition that our aperture radiates at theta max is equal to 0. So that the maximum radiation is the axis of 0. Many apertures fulfill this even if E0 is not constant. But many apertures have the maximum directivity in the z-axis. So this is what makes my life simple here. I'm just making space here on the board so that I can proceed. So this is always true when I have the maximum radiation in the direction of the axis z, which is frequently the case. Not necessarily E0 is constant. What happens if E0 is constant? So the example E0 is constant. What happens then? What is the directivity? Is 4p over lambda. And I have here, on top, I have E0 times A. The integral is very simple, it's just multiplication. Absolute value squared. And in the bottom, I have E0 that is constant, squared times A. What I get here is that 4p over lambda times A. And we proved this difficult relationship, you remember 2 weeks ago. I just pulled this out of my pockets. I say this is valid. This thing is exactly valid when we have a uniformly illuminated aperture.
Is that lambda squared? Or?
Yes.
Lambda squared here, yes. Thank you for telling. Lambda squared gets from here, lambda squared here, lambda squared. I forgot the square here. This is always valid for apertures that are constantly illuminated. So for constantly illuminated aperture, this formula makes a sense. What happens if the aperture is not constantly illuminated, but still maintains its maximum radiation in z-axis? Then this thing here probably gives you, in the general case, gives you somewhat less, because you see, this term here is unimportant of the phase. Here the phase is unimportant because we always take the absolute value, and the absolute sign kills the phase. So here we have a power sum, while here we have a phasor sum. A phasor sum is dependent on the phase of E0. So if we have a phase error on our aperture, we'll get less. Also, if we have some amplitude distribution, this integral will give less than this integral. So in the general case, this thing here, sorry, I have to make space on the board. This expression gives us less. And in the general case, we simply rewrite this equation and we say that directivity is 4 pi over lambda squared times the effective area of our antenna. What is the effective area of our antenna? We can derive it out of here. The effective area of our antenna is simply what is left over here, is simply now the absolute value of the integral of E0 x prime y prime dA over A squared divided by the integral over A of the absolute value of E0 of x prime y prime dA. This gives us directly the effective area. So this thing here is just the effective area of our aperture. Effective area. And this is now an important term we are going to discuss. This is the A is the real size of our aperture. Effective area is the actual area that is actually takes a role in this equation here. We could also rewrite the same equation as the directivity is now 4 pi over lambda squared times illumination efficiency times alpha effective. So illumination efficiency, I usually write it as eta prime, and not alpha, times A, times A. So or in other words, my effective area is now illumination efficiency times A. So this is so what does this term tell us? This term tells us that illumination efficiency does not mean loss of power. We are not hitting anything with resistive losses in this antenna here. Illumination efficiency means just how good we are to approach, how good we were to approach a constant illumination. Usually we cannot obtain a perfectly constant illumination. And of course, we can rewrite the integral for the illumination efficiency here as the true efficiency, efficiency. So A here is E aperture of x y prime dA squared divided by real aperture times integral over this aperture E0 of x prime y prime absolute value dA. Or in other words, this is effective area over the real area of our aperture. We shall see next week what values can this illumination efficiency achieve, what values can A effective achieve with respect to A. This illumination efficiency will be something that we are going to work for, to get the best possible directivity or gain out of our limited aperture size. So we would like to illuminate this uniformly, constantly, but usually we cannot do that. So we are going to deal with this efficiency. Of course, the efficiency should not go over 100%. Usually, for such a horn, it's between 50 and 80% for such a horn antenna. This illumination efficiency. This illumination efficiency is not loss of power. There are no resistive losses in our aperture. We have no lossy media in between here. This is just how well are we using the area of our aperture. How good were we at making the most of the size of our antenna. I hope that makes sense. Next week we will have a look at horn antennas as the most stupid antennas we can make, but they're a good example, and they're also sometimes good in the lab.